Great. Okay, thanks, Francesca. We saw also your question, Chris, so we'll answer to that soon. Sorry, we missed it before. Okay, so just before starting, a couple of announcements. So the toilets are just very close to the door, so just exit this room and then just go straight left, just in front of the entrance. Okay. About lunch and coffee for tomorrow and later will be just served outside the room. Okay, so just help yourself with food, coffee, whatever. If you want espresso, you can just go upstairs and enter the kitchen, and there is a DeLonghi coffee machine that makes espresso. So if you're a bit fussy about coffee, you can just go upstairs. Okay, and I'm more than happy to show you how it works. Okay, so let's start again. Chris, please.
Thanks, Lorenzo. Yeah, so Chris Sherlock Online posted the question, should the memory wall affect how we write, for example, C++ code? If so, how? Or does the compiler take care of this for us? And of course, the obvious answer is it depends. I think, so the first thing to note is in this little C snippet that I've got, what we're actually doing here is we're chunking through two arrays of data, so A and B, and we're actually stepping over those arrays in units of 8 32-bit single precision floating point numbers. Okay, so each floating point number is 4 bytes, so 32 bits, and we're taking 8 floats at once. Okay. The way that C pointer arithmetic goes, what we're actually having to do here is take a chunk of 8 floats that are arranged contiguously in memory. And what I'm going to talk about in this sort of second half an hour, 45 minutes or so, is the need to make sure that your data is contiguous in memory and not scattered everywhere and like a bunch of class instances all around the place. Okay, so that's point one. Point two is that in this very simple case, I would expect, using the optimization flags in GCC, for GCC to kind of work out what I'm doing and automatically vectorize the code. Now, the reason why back in probably 2015, 16, I wrote this code is because I found out that actually that auto vectorization wasn't happening. And so and that's why I was looking at the assembly code, because I wasn't seeing these XMM registers being used. And as soon as I kind of manually vectorized it, A, I got the speed up that I expected to, i.e. times 8. And B, I started to see proper vectorized assembly being emitted. So I think the answer is your mileage may vary. The advantage of using the accelerated libraries, like, for example, the eigenlinear algebra library or Armadillo in C++, or PyTorch, TensorFlow, JAX in Python, or an optimized BLAS library used in R. So the advantage of using those is that they will automatically vectorize the computations, providing that you've given it data stored contiguously in memory. That's the central thesis. So yeah, I think, be careful what you're doing if you're using kind of slightly lower level languages. But I think, modern maths libraries, as long as you use them correctly, should just do this off the bat. Hope that answers the question. Okay, so back to Tamash's question. Well, what have the registers got to do with cache in CPU? Well, we said that registers are kept right next to the arithmetic logic units. They're kind of hardwired in with, well, not bits of copper, but silicon channels. and they're about the quickest memory access that a CPU can possibly do. It takes 1 clock cycle to retrieve a register or to store a register. Okay. But it takes potentially many hundreds of clock cycles to fetch in data from RAM. So the halfway house is this kind of hierarchical arrangement of cache memory within the processor. So typically, in fact, this is a bit out of date. Typically, modern CPUs will have 3 levels of cache these days. And the idea is that as you go up the cache levels, the data gets closer to the processor, but you get less cache. Okay, and the idea then is to use commonly used data, keep that in the cache. When a processor needs a bit of data that's not in the registers, it will look at the level 1 cache. It will say, does this data exist? If it does, it will put it straight in. If it doesn't, it will go down to the level 2. Does it exist? If it does, it will put it up a level, and finally have to reach out into the global RAM. Okay, so the idea then is to really kind of, if you're doing kind of like a matrix vector multiplication, we're using bits of data multiple times. Those bits of data we use multiple times, we try and keep as close to the processor in the cache as we possibly can. Now, obviously, there are electrical connections between the CPU and the registers, between the registers and the cache, and the cache and the RAM. Okay, and what we can't do is just move data any old how between slots in the RAM and slots in the cache, slots in the cache and slots in the registers. Okay.
Yeah, question. So in the scheme that we showed, I don't know, half an hour ago, the cache would be something separate on the outside.
So the cache, yeah, that's a good point. Yeah, that one. Yeah, so the cache would be sat. That one. So the cache would be sat inside this yellow box. Yeah. Yeah, notionally. So it'd be sat close to the registers, but not as close to the logic unit as the registers are.
Okay, and you will reach the data between the cache and the register.
Exactly.
Then,
Yeah. And the way to think about it is, fetching data from the cache is a lot faster than fetching it from global RAM, but not as fast as fetching it from registers. So you get this trade-off between quantity and access time, essentially. Okay. Yeah.
When you say it's like becomes variable of expense for each of the things, how are you measuring that expense?
Clock cycles. Yeah. So it doesn't really matter how fast your CPU is running. If it takes 100 times longer to get data from the RAM as it does from the register, well, maybe it takes 4 times as long to get it from the level 1 cache as it does the registers, and maybe 10 times as long from the level 2 cache.
You also have like limitations on how much cache you can put on it.
Yeah, exactly. Yeah, because I mean, if you think about your machine, well, the old 6502 processor, we actually had no cache on it, was a chip that was about that long and about that wide and had a very countable number of pins coming off it. Whereas, if you take a chip from kind of the early 2000s, like an Intel chip, it was probably about that size, and you turn it over and it had pins around the edges. And now, if you take a chip, they're a bit bigger, turn them over, and they've got pins all over the place. And really, it's that sort of physical size limitation, the kind of sort of 45 nanometer, 22 nanometer, 12 nanometer technology that they're etching these chips with nowadays is all to do with cramming it all into that small place and then dissipating the heat. Yeah. And that's generally why processors with more cache get more accuracy in manufacturing involved. So that's cache. But what do we have to think about in order to get memory from the RAM into the cache and cache into the registers? We have to think about 2 things. One is the concept of alignment, which I think is probably the second order problem as far as we're concerned. And then the most important one is, as we've said, data contiguity. Okay. So why is this a problem? I like to think about computer memory as the library. Okay, so if I go to the library and I want to get a bunch of books, and those books are all kind of scattered in different parts of the library, I've got to kind of hunt around, going to different places, spending time moving, looking along the shelf of the book and pulling it out. Well, if all my books are, kept in like the, I don't know, the crystal crazy computer architecture bit, I can just go to that bit and sort of pull out the books that I need straight away, and I only have to do one trip, right? So caches kind of work in the same way. So data from, let's say, the RAM is fetched in fixed sized units. And the size of that unit depends on the processor that I'm using. So if for like a typical Xeon, Intel Xeon CPU that's sat in a server, let's say, then your cache line size, so the sort of atomic bit of data that's moved in and out of the cache is 64 bytes wide. Okay. So it's a bit like going to the library and picking up a stretch of books corresponding to 64 bytes. Okay, picking it off the shelf, taking it away, using the book you need, picking them back up, and then going and putting them back on the shelf. Okay. Now, if all my books of interest are distributed throughout the library, I've got to do a lot of running around, picking up my 64 bytes worth of books and carrying them back to my workspace, getting the book I need, taking it back. Okay. But if all the books were co-located in the same place, and in the limit, if all the books were side by side on the shelf, then I could just get all the books I want in just the one fetch, right? And so it is with processors. So to maximize, so really what we want to do, given that RAM is really expensive, we want to minimize the number of accesses that we do. So we can do that by making sure that our data is all lined up next to each other in a big long array, and then just fetching blocks of that data as the CPU demands it. Okay. And what this effectively does is it reduces the number of cache misses. And the cache miss is where the processor goes, I want a bit of data. It looks in its cache memory and it goes, oh, I haven't got it. I've got to go out to the main memory and fetch it in. Okay. If I've got the typical kind of linear algebra style algorithm where I'm just kind of iterating over data, then actually, the chance of me pulling in a bunch of data for the first, a cache line for the first item of data, going back and seeing if the second item of data is, then the chance that I have that data already in cache is massively increased. Okay. So this is the importance of having data contiguously in memory. And the example which, given the time, I don't think I'm going to show you today, but I might do later on in the week, was of this kind of sort of agent-based simulation I'd written in C, C++, for foot and mouth disease in the country. And I thought I was really good writing this thing, and this nice sort of idea of having a class that represented a farm, and then multiple objects of that class representing different farms, and then you have a for loop which iterates all over the farms, that kind of thing. Very nice, reasonably clean code, but ran really slowly. And then when I started thinking about GPU code, well, the first thing that happens when you read the NVIDIA CUDA C programming guide is it says, you must arrange your data contiguously in memory. Okay, fine, right, so massive recode. 3 months of messing about, learning about GPUs and implementing this stuff. And I got an algorithm that ran 380 times faster than my previous grad code. Great, awesome. Okay. Then I went back and applied the GPU principles, memory contiguity, to the CPU code that I'd written. And I employed the vectorization techniques and I got an improvement in my C++ code that meant that actually now the advantage of using the GPU was only about 2.5 times better than my new bit of C code. So this really does matter. And I kind of see this time and time again in students who, put together one of these simulations in a very kind of intuitive way without knowing anything about the architectural constraints in a computer, and come to me and I look at that code, and I go, this is running really slow. You say, oh yeah, I've done 500 iterations of MTMC and it's taken me a week. You go, okay, how about recoding it like this using, kind of arrays, vectors, matrices? All of a sudden it accelerates their code and they're amazed by it. And that keeps me in employment, apparently. It's a cheap trick.
This kind of stuff is like the orient the design type principles, right? These like design.
Very much.
Systems, so,
Well,
do you think that
yeah.
much with these kind of principles of the
Don't say again.
do you think there's might conflict a little bit with some of their rough ideas behind them?
No, I think they're very good bed mates.
Okay.
Yeah, I'm going to. That's all I'm going to say because Darren's going to take over, but I don't think it conflicts at all, actually. Right. Okay. So now what I was going to talk about in the last half an hour, really. Let's get down to brass tacks and talk about parallel architectures and the useful pros and cons of different machines and kind of what's out there. And really, I'm just going to sort of think about CPUs, standard architectures that you'd find in your laptop or a server. There are a couple of little wrinkles, this sort of comparison between SMP machines. I don't know if you've ever seen the initials SMP stuck on the end of the Linux kernel, for example, but symmetric multiprocessing versus this non-uniform memory access. We'll talk a little bit about that, and again, in the context of getting data into processors. Then I'll talk briefly about GPUs. I'm not going to go hugely into this. We've sort of talked about SIMD architectures, and GPUs are really just a generalization of SIMD. And then we'll just chat then about clusters and how clusters can combine SIMD implementation within Node, either on a CPU or GPU, with then swapping information between themselves over the network. I'm not going to tell you how to do this. I'm just going to describe the hardware essentially. Okay. So as I said at the beginning, all modern computers, including your
Maybe on the cameras. You don't mind?
oh yeah, sorry guys. Thanks, Sam. Yeah, so all modern computers, including your mobile phone, have CPUs and have typically these days multi-core CPUs, potentially with vector engines on board as well. There's a bit of a buzz really in mobile development at the moment, and a lot of mobile developers are turning to kind of very highly optimized BLAST libraries to help them kind of use machine learning models and things just on a device, really kind of trying to screw the power consumption down as much as possible. And we can make use of this. And, as I've just said, well, working at the high level, at the kind of the Python level, the R level, what we're really wanting to do is make use of these kind of parallelized basic linear algebra subsystem libraries, BLAST libraries. And there are quite a few of them around. Popular one at the moment seems to be OpenBLAST, which was formerly GoToBLAST, drove a Japanese computer scientist almost to the brink of extinction, I think, hand optimizing this. But then, of course, there's the mass kernel libraries as well from Intel. Compilers, just going back to Chris Sherlock's question, compilers these days should be able to recognize when they can vectorize code, but typically that relies on us producing very kind of clean code in which we make sure that we're doing the best that we can to arrange our data in array data structures. And then there are a bunch of high performance libraries, and I particularly like Eigen. So if you look in the kind of the JAX internals and the TensorFlow internals, you will see the Eigen value, the Eigen library used for an awful lot of the linear algebra that goes on. And Eigen kind of looks after data contiguity. It makes sure that data is aligned to the kind of the fixed slots where your cache lines fetch data. So you can think of those like your shelves. And it invokes the vector engines and that kind of thing. So if you're a C++ programmer, I very much recommend Eigen. I think it's got Rust bindings as well if you work in Rust. CPUs, well, they're easy to use. That's just what's there in front of you, right? So if we can use these libraries, then why develop on anything different? Just remember that the SIMD principles apply just as much to a CPU as they do anything else. Multi-core processing, again, multiple CPUs on the same machine. Well, again, if you use kind of parallel open blast or you use TensorFlow, JAX, etc., they will just use the number of cores that are sat on the machine. And particularly TensorFlow and JAX are very good at making a decision over whether using 2, 3, 4 cores and managing the potential contention with them is more advantageous than just running more iterations on a smaller CPU. So you get this very sort of elastic compute that uses more or fewer CPUs as the subsystem thinks is sensible for your given problem. If you're working in C and C++, then all the compilers out there, particularly the ones that we use commonly, so Clang and GCC, if you've used that, they all have directives that you can insert into your code just above, for example, a for loop that instruct the machines to parallelize that for loop over however many cores that you want to. So it's quite a straightforward kind of low entry barrier, I guess, thing. The problem with multi-cores, and again, we're going back to the foot and mouth code, which I could never quite get to scale beyond about 32 CPUs sat in a machine with this very expensive Sunbox that I got a day to try. Is that really because all the cores are trying to access the same bits of memory, at some point you get this kind of queuing up for the memory bus, and scalability of your algorithm starts to go sublinear. Okay. Just a word about non-uniform memory access. So most kind of low-end machines, so this laptop here has got it's got on it 6 cores, I think. Most low-end machines are what we call an SMP architecture. An SMP architecture really do have these memory bus issues. So all the CPUs, here we've got 4 of them, are connected to the same memory controller, and then the memory controller just is connected to the RAM, and it just fetches the data and it passes it back through this kind of bus channel up here. And this bus can get saturated. It's like having too many people at the bus stop trying to get on the bus. Actually, there's a queue that develops. So the way engineers have tried to solve this is with this so-called non-uniform memory access pattern, where each CPU gets its own dedicated block of memory. And actually on some of the high-end motherboards, you can even see this in action because actually the CPU is kind of spatially co-located with the memory. And so the idea behind this is it reduces the contention by divvying up the memory and attaching it to specific CPUs. The only problem is that if a CPU needs the data that's in another bit of memory somewhere, it's got to ask its neighboring CPU for that data and incur a performance penalty in doing that. Okay. So really, it's all about then distributing your data close to the core that's going to use it. Mostly that's done by the compiler. I've never done that manually, believe there are directives within GCC, for example, in C that will allow you to do it. I certainly don't think you can do it in Python. And yeah, most of the time it's just kind of up to the operating system and the compiler to distribute that memory around to where it's being used most often.
So Scott, how does this contrast with the stuff you were showing earlier with the action and so on, where it sort of?
Yeah, sure. So each CPU still has its own cache and registers inside the blue square, essentially. Yeah, yeah, exactly. Yeah. So this is reaching out into the global RAM.
So actually, Jackson has specific instructions to feed data to
Yeah. Okay.
that X maps that
Yeah. Right.
essentially.
Yeah. Okay. Yeah, I stand corrected then. Thanks. Yeah. Okay. So that's CPU. We've done SIMD processors now, right? So GPUs are just massive SIMD processors. So our GPUs in the high-end computer here are a bit old now. They're NVIDIA V100 cards, but they've got about 3,880 thread processors on them. So, process 3,880 bits of data simultaneously. GPUs differ in the engineering principles compared to CPUs. All the manufacturers tell us is that they have more transistors on them that are kind of denoted or devoted to doing data computation, as opposed to moving bits of data around. So the reason for this is that CPUs are very general purpose entities, right? They can do mathematical computation for us. They have to deal with I/O, disk access, getting data from memory, deciding on security, deciding on which operations to put ahead of other operations in that kind of pipelining thing. So a lot more of the space on the processor die is actually taken up by that kind of sort of, kind of management electronics, if you like. Whereas GPUs, the processors are in a way much more simple. They do away with a lot of that kind of data management craft. Why? Because GPUs kind of assume that you've aligned your data kind of contiguously in memory, again, that it's kind of got this matrix structure to it. So all they need to do is to be able to reach out, grab an arm's length of data, big cache line, lob it into their cache and crunch on it. They don't need to be managing the data quite so much. The big sort of shot in the arm for me when I started using GPU compute is that communication time between threads on a GPU is tiny compared to even communication between CPUs on a in the host and on a motherboard, let alone kind of clusters of computers. So I think the real advantage that GPU gave us kind of sort of 10 years ago, 15 years ago now, was combining massive parallelism with very, very low communication latency. I think for these kind of sort of, if you can cast your problem as a linear algebra, then GPUs are definitely your friend. Even things like MCMC algorithms, where often the rate limiting step is the likelihood computation itself. So being able to very quickly compute the likelihood in parallel and then do all the little serial steps that you needed to do on the next kind of parameter proposal and stuff, actually it works quite well.
What is the, maybe we'll talk about this, but the fact that it's so cheap to communicate between threads, what's a simple example of where that comes up?
Yeah, so supposing you want to multiply two matrices together. So what you might do is you have a bunch of very low power, a bunch of Raspberry Pis or something. Then you might divide that matrix up between the two matrices between the processors. Okay, each of those processors would do its little bit of the memory, and then of course they have to communicate because there are summations that have to be done, kind of thing. So take a chunk of matrix, do your computation, then squirt the result down a very slow network to a node that's going to do the summary. That makes kind of network-based cluster computing really slowly. Whereas on a GPU, as long as you can fit that matrix into the GPU's memory, actually, when you block the matrix up into blocks of threads, those threads can compute their summary statistic, stick it into cache memory. Level 2 cache, because level 2 is shared amongst the symmetric multiprocessors. And then they just kind of work directly on memory with no network involved or anything. There's no memory controller involved as such.
Thanks.
Cutting out the middleman, I suppose. Yeah, okay. So yeah, to follow up on that, this is what this looks like. So GPUs do have a memory hierarchy. GPUs are kind of divided into these sort of streaming multiprocessors, in which you get varying numbers depending on how much you paid for your graphics card, effectively. These days, particularly in the NVIDIA world, all the most multiprocessors have registers. So threads that are running within the multiprocessor have access to all the registers. Okay, and they also have a level 1 cache. And some read-only memory for things like constants and that sort of thing. And then all the multiprocessors can reach out to the level 2 cache before having to reach out into the global video memory, okay, the GPU memory, to get data if it doesn't exist in cache. Okay. And kind of, I suppose, bound up with that statement that GPUs have more transistors dedicated to data processing than sort of data management, is that there's a strong mapping from the position in the global memory to the position in the L2 cache, and then from the L2 cache to the L1 cache, and so on and so forth. That's much less flexible on a GPU than it is on a CPU, compounding the need to lay the data out in the right kind of way to enable the GPU to take advantage of it. And again, this idea of contiguity. So, yeah.
That's from mapping means that you can shove data from global to GPU, but just much faster.
Yes, than you would have been able to if there was a conventional memory control in the way. Yes. Yeah. All of that circuitry is kind of simplified because of this idea of assuming the data that you're working on is kind of matrix data rather than scattered all over the place.
Like play it in the same box and you get the advantages of.
So the big thing with GPU programming in general is that GPUs are separate from the rest of the machine. Right? And if you're a gamer, you buy your GPU on a PCI card and you slot it in the back of the machine, and you might have to add some extra power. But basically all the communication then goes over the PCI bus in the computer. Okay. The PCI bus is kind of like getting in your car and driving down the motorway to the next town as far as the CPU is concerned. Okay. So PCI bus contention, bus saturation is a big issue in GPU programming, and this one really does bite us at the Python level as well. So again, beginning of the pandemic, I was looking for a way of not having to write armfuls of CUDA code in order to implement my COVID model. So I chose TensorFlow, and my first incarnation of it, actually, it gave me some speed up, but I was a bit disappointed. And then I worked with the guys at Google Research who were developing TensorFlow, and they said, well, okay, actually, if you reorganize data in this sort of way, all of a sudden I'm going to orders of magnitude speed up. And it's because of this idea. If you write an algorithm that does something on the CPU, then has to send a piece of data across the PCI bus before the GPU does its work, and vice versa, then you incur a big latency across the bus. Now, the PCI bus is a parallel bus. Okay, so the more data I can save I can send through at once, the more kind of width of the motorway I can use per kind of invocation of the bus transfer. So you can mitigate this to some extent by sort of increasing the size of the memory transfer you do. But if you're doing it often, it will seriously damage the scalability, the parallel scalability of your algorithm, because it's essentially a serial operation. So really the take-home message from this is, if you're using a GPU, then make sure that you do as much of the work on the GPU as you can to avoid data being transferred over the PCI bus all the time. And well, certainly TensorFlow gives you this lovely kind of TensorBoard profiling suite where you can actually look and see if that's happening. And if it is, you can kind of think about how you can change your code in order to stop that. And generally, it's about kind of bundling as much data as you can into one data structure and then only operating on that one data structure. So yeah, so the thing to watch out for with the GPU, PCI bus thing, it means that GPU algorithms will typically work best if all your compute is sort of relatively suited to a GPU. I have been known to write MCMC algorithms on a GPU where it's been more efficient to run a parallel function on the GPU and then for like a likelihood, and then just to run a single thread job to do a proposal on the GPU and then go back to the likelihood, than it is to compute the likelihood on the GPU, retrieve the result onto the host, do the accept reject ratio on the host, and then push the result back to the GPU. Okay, so they really are quite slow things, PCI buses, even in higher end servers. To some extent, this has been mitigated. I said I'd have a quick shout out for the N8 Computational Intensive Research Theme Tier 2 supercomputer that is in Machine at Durham called B. So this is a special architecture. It's an IBM kind of proprietary thing. It uses IBM's Power 9 processor. It's not an Intel processor. But the point is that they've got GPUs on board, and the GPUs and the CPU all share the same memory space. They don't have a PCI bus in the way on that architecture. And to some extent, that kind of solves this PCI bus problem, but it doesn't completely alleviate it. Okay.
We do expect that to become more normal in these things with the new
Yeah.
True.
Yeah. We'll see how it goes. Okay. So finally then, clusters. Okay, so how do we use a cluster? Who's used a cluster? Usually more people have used clusters than HPC than GPUs. Okay. Yeah, so clusters are what you might think of as more your sort of traditional high performance computing environment. So this is where we have clusters of generally compute nodes that are all connected together by more or less expensive network. And then really you access, and they're all connected to a shared file system so that nodes can kind of, communicate via files if necessary. And then you have this front-end login node where you use a terminal on your machine, and you kind of log into the node, and everything text-based in general. But what are these really good for? Sort of haven't put the advantages of the HPC up front, and I should have done. Because you can essentially have as many computers as you like, up to sort of sensible limits, but you can have large numbers of separate computers. HPCs are really good when you've got very, very high memory jobs, because you can distribute memory over discrete units. Right? So, for a particular box, well, rumour has it our Vice Chancellor has a computer that has 2 terabytes of RAM, which all processors can, access. But that's about the limit, I think, RAM I've seen on in a discrete machine. So by distributing the memory over the cluster effectively, you just kind of add more nodes and just increasing the mix to redundancy. The disadvantage, as we said, was that actually those nodes now need to communicate, and they have to do so via some sort of network. And the way in which you connect those boxes together really determines ultimately the speed of that communication. And because we view communication as kind of a serial operation, therefore it determines the ultimate scalability of your algorithm in terms of the number of processes. That said, increasing amounts of RAM on boxes, increasing number of GPUs on boxes, increasing CPU SIMD computation, it kind of meant, I think, that each node can do more computation than it could do in the past. So actually the amount of data and the number of nodes that are needed in your kind of cluster of machines is actually probably smaller than it was. So the amount of communication is less. And sort of to take advantage of machines like that, well, either you use them for kind of this embarrassingly parallel computation where you just set out lots of algorithms going. Supposing you wanted to run 4 parallel chains on an MCMC, well, just set an MCMC running on each box, that's fine, just collect the results at the end. Or you can, particularly physicists like doing this, you can come up with algorithms that are specifically tailored for HPC, where, for example, n-body simulations will kind of assume an approximate independence between bodies in the simulation and reduce communication that way. So I kind of think, you know, it would take another week to even just go into kind of HPC really. So I just wanted to kind of skim the surface of this. Modern libraries, so I think particularly JAX has got this really well sewn up with the PMAP command for mapping the data amongst different nodes over a network. Works quite well. I mentioned Python Dask at the beginning, the kind of sort of single program multiple data paradigm. That works very, very well in clusters. The earth scientists love using Dask because they can use up the cluster. Typically what they're doing is doing embarrassingly parallel processing of very, very large raster images, which can't be held in RAM. So for them, you know, a cluster which bites off a little bit of that raster, does its computation, saves it somewhere else, works really, really well. I conjecture for most of the algorithms I think we think about in this group, I'm going to say that communication is probably important. But that's what we're having this week. Okay. So in summary then, so parallel architectures, I think really it's kind of, you know, horses for courses, to use a hacky phrase. So I think, you know, if you're doing embarrassingly parallel Monte Carlo simulations, HPC clusters are really, really useful. If you've got very kind of linear algebra type jobs, or you can recast your problem, your algorithm as a linear algebra problem, then GPUs are great. CPU compute is great, particularly for, you know, workloads which genuinely need a lot of kind of non-contiguous memory fetches, and they're better built for doing that. But we've all got CPUs on our laptops nowadays, and the sort of problems that I can solve using the high level, the Python libraries, JAX and so on, I think are, you know, I can do an amazing amount of compute just on the CPUs on this machine without even going near the GPU. And then it's probably less relevant to this group, but there's an amazing amount of conversation at the moment about energy efficient phone apps. And, you know, again, your mobile phone will typically these days have a graphics processor on it as well as a CPU, and establishing a balance between GPU and CPU compute for these kind of sort of, you know, AI models that people like to embed in the smart devices seems to be a really hot potato in terms of energy efficiency. The other thing is there's courses for horses. Right, and I guess one of the points of this week, if it's not completely kind of taking the methods that we've constructed over the last few years and trying to create, kind of computational solutions with them, is going the other way. Well, given that we've got these parallel architectures, I think parallel computing is so ubiquitous these days that it doesn't really make sense to think in serial from the get-go. I mean, I've been parallel computing for a while. I tend to think in parallel these days. So there's very little I do that's not parallel. But if we culture that kind of parallel way of thinking, couple it, in my opinion, with the functional way of thinking that enables computers to prove things like independence across data structures, then I think we can make better of the hardware that's in front of us. I suspect, another thing I got pulled into the other day was a forum on sustainable computing in the Northwest. I suspect if we did this, we might find that the energy cost, the carbon cost of our algorithms decreases as well. And I think that's something we're going to have to think about for the future. And lastly, it's all there. We can access all this technology in universities, go and experiment, see what works. Thanks.
Chris. So we'll have a break and start again at 3:30 with Darren. Okay. Hopefully coffee will be outside. We'll see.
Are there any questions or comments?
Oh yeah, questions or comments? Sorry. Yeah.
Yes, I'm just wondering what type of things would happen, like when you talk working on a GPU and you need to communicate with something outside of the GPU. Like the only thing I can think of a problem will be if you cannot fit the data on the GPU RAM, right? But is there something else that you've noticed where you need to communicate outside?
So probably not, no. But I/O is the big one.
Okay, yeah, so bringing software, we're logging.
Yeah.
Okay.
Thanks for the interesting. It's probably, frame this question properly. There's quite a big emphasis in you talk about sort of memory and how to organize those structures and how good the memory to make it efficient in terms of the process. But one of the discussions you mentioned that any distinction, maybe it's not necessary, I think that's why I'm asking. Between the process and the thread, you use the word thread a lot.
Yeah.
Process hardware tool.
Yes.
And a lot of embarrassers in parallel computing is still going to process,
Yeah.
which has ramifications in terms of duplicating data.
Yeah.
So, yes, and also sort of bottlenecks in terms of data processing. So,
Yeah.
Is there anything that do you have to worry about that in the context of code? About it, or is the concept of just using threaded code?
Sure.
The main issue.
Yeah. So I think it goes back to the setup and teardown costs and the way that they kind of impact on Amdahl's law. And so a processor is an entire computer program that gets loaded into memory along with all its data. And there's some setup cost, often non-trivial setup cost involving disk access and that kind of thing to spawn that process up. What you wouldn't want to be doing in your parallel algorithm is spawning those processes up and tearing them down kind of on the fly. Definitely not. Single process, multiple data basically says, okay, we're going to have multiple copies of that program, but we're going to start them up at the beginning. We're going to amortize that setup cost across the entire cluster. And then those processes just stay running for the entirety of the algorithm and tear everything down at the end. I think, so threads by comparison are kind of, you think about them as light processes, which, there is some setup cost to them, but it's much, much less than spawning up a big process. Some of the high level, very high level scripting languages I think there are parallel libraries in Python, which I'm less familiar with, but will actually fork the R process when the parallel section of the algorithm begins and incur a massive performance hit. And I just wouldn't recommend using those packages. So I think that's a thing to remember.
Predominantly used to our sort of.
Yeah, right.
Stuff in the least efficient.
Yeah.
Exactly, in terms of. Doing the most of them.
Yeah.
Which clock cycles are that. But it's exceptionally easy to implement.
Yeah.
So there's a trade-off between what would take me 3 months to rewrite the code and what you said is when you start versus just long processing and waiting.
Well, I kind of hope that by Friday,
We might have changed that.
we might have changed our tune in terms of the languages we program. Right. And I think these days I wouldn't be rushed through these and recommend anybody start C in the way that I did when I was a PhD. That's what we had. You know. So yeah, I'm definitely steering things towards Jack's post-running outsourcing.
Thank you.
Yes.
Any other question? Wendy?
Yeah, so going back to some of your earlier slides on Amdal's one, so you had this, it was kind of like a 1/m scaling, right, roughly? With
Yes.
So was it the thing process?
Slide back.
I have one, I mean,
Sure.
my question was basically, is there a version of this that also takes into account, say, if there's some stochasticity in the system? Because you can imagine if, say, going back to the Navy comment, if the runtime was, say, the number of clock cycles actually could vary, then you could be in a situation where actually morphle slows things down because you're waiting for the longest one to do the slowest one. So I want to know if there's a version that takes that into account.
I reckon that.
No, I'm not seeing it written down. I mean,
No.
it absolutely is an issue.
Yes.
See it in the SMC resampling, for example. Yeah, there is SMC threads and you are waiting for the slowest one that gives you around they can variance. But I'm not seeing anybody actually write that.
I guess the thing is to sort of think about, you know, what would be the proportion of the time for which, say, impoverishment occurs. So how much of the time would you be waiting around for that one process to finish doing its job? I mean, it's a real concern. It's a massive concern for rejection sampling based around the number generation on GPU. What really there is, for example, and I know kind of there's been some quite clever work come out of Oxford from my Jonathan group on how you kind of mitigate this issue of, you know, your training process that's just throwing its die and never kind of accepting it. And what can you do about that? But yeah, I mean, I guess you could embellish a lot. But I think the idea of just thinking about those kind of training processes with serial executions is the way to apply it.
Any other questions?
So suppose you're going to implement a embarrassing parallel, then probably it won't be very. You don't have much incentive to actually optimize it with the GPU parallelization, right? But you probably want to do some parallelization within the CPU. Okay. So the mix very well if you're run some multiple cores while using.
Yeah. I mean, I think it's kind of one of those things where, you know, it is going to take you longer to implement a parallel algorithm in general, because you've got to think about the problem a bit more carefully. Whereas, as you say, if you've just got an embarrassing parallel thing to do with an R script that is fast enough, then throw it at the cluster and, you know, that's fine. Get your answer. I guess where I push back is delivery of products into industry, particularly, which is what I care about the story thing. But also kind of just carbon tax that's involved with inefficient computation. It might be very convenient for us to just kind of, you know, write an algorithm that runs fast enough for us, but supposing somebody picks that package up and they run it millions of times. And actually, the ratio of kind of code interpretation or non-new data around to actual computation is 1%. Well, quite a bit of carbon tax.
I guess, yeah, last questions.
Yes, so like you've been talking a lot about how the GPU, for instance, like processes data, but you've not really mentioned how the GPU is being processed itself. So like all the controls for that
No.
arises.
No, absolutely not. So this was very much, this is what the hardware is. This is what you might think about using. The controls are actually driving the GPU. Do we even have a session this week on that? I'm not sure we do. No, so that's the kind of masterclass week.
All right, guys, I think the question is off if we want a coffee break, otherwise we make discussing all okay, discussing. So yeah, coffee hopefully outside. Another thank you, Chris.